So far we've looked at linear regression and GLMs, and we really need things that will deal with more complex response curves for each predictor. So in other words, most natural phenomenon doesn't respond in a linear way, nor does it respond in a way that can be modeled by a logistic. An awful lot of the phenomenon that we have will have some kind of an optimal point, and then it'll ramp down on one side and ramp down on the other. So we see this with abundance, diversity, and a lot of other characteristics, or a lot of other phenomenon where it just doesn't work out well at a low value. It has an optimal value, and then as the optimals increase, things get worse. We see this with things like temperature and precipitation and other phenomenon. So to get something more complex, we move to higher levels of math, but not too high. Don't panic. They should look familiar, should look a lot like GLMs. The only thing that's really changed from a GLM is instead of having a number here, a beta, for a coefficient value or an estimated parameter, we now have a function. And I think this is actually pretty cool. We can take a function, apply it to our covariate, and modify it so that we can have a linear regression equation. And if you take a look here, this is again just like GLMs, where we've got our estimated value of y with our inverse link function, and then we've got a function applied to each of our covariates. Another cool thing is the function can be parametric or non-parametric. We'll use splines within GAMs, which is non-parametric. They're very general. You'll see literature where it talks about them being prone to overfitting, which is kind of funny because Maxent is massively overfitting, as is can massively overfit, as can some of the tree methods like boosted regression trees, and they can do much more overfitting than GAMs ever can. So GAMs aren't overfitting too much, but you still need to control for it. We'll talk more about that. All right, GAMs use spline curves. And spline curves are pretty cool. They're nonlinear, as you can see. They can represent pretty complex dynamics between predictors and response curves. This is the math. We don't really have to worry too much about that. What you do want to know is that there are knots. That's important. Okay, the more knots, the more complex the curve can be. Okay, the knots are the points along the curve. All right, when we look at spline curves in R, what you will see is this S, that stands for spline, and we wrap the predictor in a function for S. The gamma parameter is what controls the number of knots, that controls overfitting. So 1.4 is recommended, but it's something that we'll play with, and we want to play with to change the complexity of our model to fit what we would expect based on the phenomenon. And this is the equation. Looks very much like GLM, where you've got your response curve, and then you're relating it using the tilde, except now here we see the S wrapping around something like annual precipitation to give us a GAM model for height based on annual precip. And then you can just add additional covariates, specify the data as we did before, and then the gamma parameter at the end of the function call. Okay, so we have a little bit of reading in front of us. These are good to read when you have time. Element Statistical Learning and Generalized Additive Models by Hasty and Tibishiriani. This is one of the original books written about it. It's actually, you can download it. I think it's freely available. Pretty cool, and it not only goes into additive models, but other methods as well. For the next meetings, particularly this week, please read Martinez-Rancun about Wahoo and Jensen about crabs. All right, so one issue we have is which method to pick. GAMs are one that we can do prediction with. Kernel smoother is another one that will look a lot like a GAM, have very similar types of dynamics. But a kernel smoother is something where it's not really predictive because it's simply smoothing the data out over an area. It's not going to give us the kind of relationship that we're looking for, so we can try and understand the phenomenon and also do prediction from it. Okay, when we run our plots for GAM, you're going to see again a plot for each predictor variable, right? So here's annual precip. Please redo these, don't leave them like this. Okay, and the response curve is going to be familiar to you, only it's going to look more complicated, right? They can get pretty complicated, and that's the solid line here is the response curve. And this is for this one, or a partial plot based on the response based on this predictor. There's also a 95% confidence interval. Know that the confidence interval is the confidence interval for the response curve. It's not for the data, it's for the response curve. In other words, if you had similar data sets and you ran them over and over again, different data sets from the same phenomenon, 95% of the time your response curve should fall within these boundaries. Now, that's of course based on the nature of your data, and you can see how much data you have down here by this sample point, or grass, they sometimes call it. And you can see over here where we don't have as many points, you tend to get a wider response curve. Okay, now the other one that you need to change is this one over here. Take a look at this. This is our actual spline function, and that's what R puts into the graph. Please replace that with your actual response variable. Now, the y-intercept is something else we'll talk about, because with GAMs, the y-intercept tends to be all over the place. So it tends to actually center itself at 0. In this case, it's not. So don't worry too much about the y-intercept. It's taken out and handled separately and then put back in when you do predictions. But we don't tend to look at it a lot. We kind of just ignore it because it's usually okay. All right, here's an example to look at. This is brown shrimp in the Gulf of Mexico. And these are GAMs that I've run. One of the things to remember is with GAMs, you can not only do continuous covariates, you can also do categorical ones. Here we've done the seasoned. And the thing to look at whenever you're looking at any curves like this is, does it make sense? Okay, so here you can see as we go from sandy to mud, okay, you can see that brown shrimp increase. Brown shrimp are known to hang out in mud. White shrimp hang out in sand, so different species. So there is this strong relationship. Other relationships, yep, depth is important. Okay, certain depths, they are more prevalent than others. Salinity, might question why this is going up and down and then up again. That seems strange. In other words, all these little wiggly things like, not sure there's a ecological phenomenon that we can use to explain why these are this wiggly. So to get into more detail, here's some for Doug Fir from FIA plots. And if you take a look at annual precipitation, again, does that seem reasonable? Does it seem like it should go up and then go down again? Especially over here, where we don't have a lot of points, it's very wide. So I would wonder about this. I would bet that this is not accurate, that this should probably keep going because more water we get, we tend to have more Doug Fir. Now here, redwoods tend to overtake Doug Fir as it gets too wet, so maybe that is accurate, but more questionable than this general downtrend. Cold temperatures, same idea. The extents, the extreme values, we tend to have a little bit less confidence. And over here, warmest month. So that's what you're looking for. But then you take a look at something like this and like, that just seems strange that it would go up and then down and then back up. And I would say this gamma is allowing too much complexity in these curves. And remember that your AIC will look higher with more complexity. So that's where we get into overfitting. So crank up the gamma, our curves become smoother. This one still bothering me. So I'm going to crank it up more. Still kind of bothering me. So I just going to pull that variable out. Or actually, yeah, I guess I did. Yep, took out that variable. Nope, actually left that in. Okay, so what's happening here? Notice 10 to minus 10. If we take out the other variables, suddenly our annual precipitation straightens out. Kind of what we want to be seeing, right? As precipitation increases, Doug Fir increases in height. But notice the range here. Okay, we're getting a much wider range based on this one variable. What's happening is I have annual precipitation, and then I have all of these temperature ones. These are probably covarying, as might be the DEM, with annual precipitation. So too many variables, okay? That's how we're overfitting, is from the number of variables. Sorry, on this one. Okay, so if we take out some of these, reduce the number of variables, suddenly our precipitation is doing better. Then we have coldest month, max temperature, warmest month. And notice it's really these two that are driving the response of Doug fir, right? It's precipitation and temperature, especially the coldest month. And that really matches with what we know about Doug fir. They like it wet. They actually have a wide range of temperature tolerance, but when it gets really cold, especially up in Alaska, other species take over. Okay, if you go really high on the gamma, which I've seen done, they get really squiggly. And we don't want really squiggly because we can't explain it. Okay, even though your AICs will go up. Let's take a look at my AICs. Yeah, here at 1.4, we've got 57.8, 57.9, so they're going up, going up, going up. But this, in my opinion, would be the best model, the most robust. So lower AIC says we have the best fit of the model to the data. Doesn't necessarily mean we have the best model, right? Here's our lowest AIC, and these models are just not acceptable. Okay, one of the things that we'll want to do and see in your reports is model runs. So tables like this look really nice. They're easy to evaluate. Folks like them in papers because you can see, here's the different gammas, deviance explained, AIC, and then we tend to highlight which one was used. Also, you can put in here which covariates were used and other information about each model run. And sometimes papers will have 20 different model runs. Often we'll actually have hundreds of model runs before we write the paper, and then we'll put into the paper the ones that are the most interesting. So here's that one with 3 predictors and a gamma of 20. Is this the best model? Well, we need to look at it, think about it, try and decide if it is. I would still argue that we need data from up here before we could say that's our best model. All right, so a little bit about the math inside of GAMs. Here's how GAM chooses the parameters, okay? And it does it by minimizing this. Take a look. Sum of squares again, we see this a lot, or sum of squares difference, right? So here's our predicted, here's our sample data. We're subtracting it, squaring it, summing it, okay? Happens a lot. We've got the number of training points is n, degrees of freedom is x. X is going to be equal to n minus the number of estimated parameters. So more estimated parameters, less degrees of freedom. Take a look at that down here. You've got number of training points, okay, and then you've got gamma times the degrees of freedom, or n minus the number of estimated points. Basically know that as your gamma increases, this is going to penalize the model for the number of knots that are in it, okay? So it's going to want to have fewer training points to get the same value here, okay? Now, sometimes when you get really large values, the gamma will reverse itself, okay? So just know about that. It's a little bit of a strange thing within the math. And I think it's because of this negative down here. So when you get lots of degrees of freedom or large gammas, this goes negative and it does strange things. Okay, lots of additional resources out there. This is a good book. It's copyrighted, but it actually covers all of these different models, including GAMs with examples. There's some matrix algebra in there, which is really what R does well. So just letting you know that that's out there. And lots of other stuff on GAMs. Heavily used, and later on in the semester we'll move on to methods that are based on GAMs that have taken them to the next level.